Previously on Chemistry Z, our heroes were attacked by diamond and graphite. However, with the power of science, they were able to pattern the knowledge they needed to advance in their quest. But now, our heroes have reached the end of their journey and they must now face the Emperor of the Bonds himself, metallic bonding. Do our heroes have what it takes to make it back in time to finish their homework? Find out in today's episode of Chemistry Z. Here are the retrieval questions for this lesson. You know what to do. Diamond, silicon dioxide and graphite are three giant covalent structures that you need to know. Both graphite and diamond are made from carbon atoms. Graphite has layers that can slide over each other and so it is slippery and therefore it's used as lubrication. This is just a quick reminder that most of the elements that we have in the universe are metals. The purplish blue elements represent metals and the green ones represent the non-metals. The peach elements are metalloids, which have both the properties of metals and non-metals.
Interesting.
In this video, we saw how ionic compounds were made from ionic lattices, and a lattice structure is just a huge 3D network of regularly arranged particles. Metals also form giant lattices as well, except the bonds holding the ions together is the ionic bond, and the one holding the metal together are metallic bonds. Let me not move too fast now, let me break this down.
Why are you coming fast?
Here are three different metals. Look carefully and answer this question. Sodium has one outer electron, magnesium has two, and aluminium has three. And remember that this corresponds to the group number that they're in. Now think about what each of these must do to form a full outer shell. Sodium must lose one electron, magnesium must lose two electrons, and aluminium must lose three outer electrons. This means that those three elements are cations because they are positively charged ions. If that's confusing, check out this video that I did on ions. But using sodium as an example, it loses one electron so that it has more protons than electrons. It initially had 11 protons and 11 electrons, but now it's got 11 protons and 10 electrons. Remember that when you see brackets, it shows that the charge is equally spread all around the ion. That 1+ charge is all around the ion. All metal atoms form cations when they become charged. That's how they complete the outer shell electrons. That's how metals react. Metallic bonding occurs between metal ions and delocalized electrons. These delocalized electrons come from the outer shell of the metal. Using sodium as an example again, it is in group 1, which means it has one outer shell electron for each atom. For GCSE, it's okay for you to think that the electrons are orbiting like this, but we saw in the video for the different atomic models that that's all a lie. Anyway, at this point, the electrons are localized, just like your local Morleys on the block. But when the electrons are delocalized, they are loose balling all around the gap. Because the electrons are moving mad like this, just like water particles in the sea, this is also referred to as a sea of electrons. Notice that there's still an attraction between the metal ions and the electrons. It is just that this isn't between one specific metal ion and one specific delocalized electron. It's between the whole structure now. It is also these moving electrons that make metals very good thermal and electrical conductors. Just like a bus and train conductor guides you on your journey, electrical conductors guide electricity through them and thermal conductors guide heat through them. The key word you have to use here is kinetic energy. When you heat up a metal, the electrons gain kinetic energy. and transfer the thermal energy along the metal. When you connect a metal to a potential difference, the metal conducts electricity because the electrons gain kinetic energy and move through the whole structure. Now we've got these two diagrams. Here are some challenge questions for you to have a go at. Do your thing. Obviously, the top image is the pure metal, which means that the alloy must be the bottom image. In the top image, the layers of atoms can slide over each other when the force is applied. This is why metals are malleable. The reason they don't break is because the electrons are still delocalized, and so they can adapt to the shape of the metal. It's almost like water, it adapts to the shape of the cup that you put it into. Finally, the atoms in an alloy are different sizes. This disrupts its regular arrangement, which is stopping those atoms from sliding over each other. This is why metal alloys are usually hard. You can define an alloy as a mixture of two or more elements, at least one of which must be a metal. Let's round up all the learning we've done in these past few videos. Giant ionic lattices contain ionic bonds and are made up of oppositely charged ions. They tend to be solid at room temperature. Simple molecular, aka simple covalent structures, have covalent bonds and are made up of a few atoms and are usually gases or liquids at room temperature. Giant covalent lattices have covalent bonds with millions of atoms and are usually solid at room temperature. And finally, giant metallic lattices have metallic bonding between metal ions and delocalized electrons, which are all solid except for mercury. And there we go, lesson done.
Fatality.
So we've finished this section on bonding and we will be moving on to chemical changes part of the specification. That's because I've already done the chemical calculations in a previous playlist. You can check that one out over here. Don't forget to collect the flashcards in the description and also the revision timetable, and I'll catch you guys in a bit.